Fluid kinematics is the study of motion geometry. We analyze the velocity, acceleration, and flow patterns of a fluid, completely isolating these variables from the physical forces or pressures causing the movement. The immediate engineering challenge is that a fluid is a chaotic system composed of millions of colliding particles. If we attempt to track a single specific particle as it travels through space and time, we're using the Lagrangian approach. While this method is highly effective for solid mechanics, the mathematics become intractable when applied to the sheer volume of particles in a fluid. This diagram illustrates the alternative. On the left, tracking an individual car represents the Lagrangian method. On the right, the Eulerian approach fixes a control volume in space, like a toll booth. We observe fluid parameters strictly as particles pass through our designated boundary. For all fluid mechanics problems you encounter on the AEE or GATE exams, this Eulerian spatial control volume is your default operational framework. By abandoning the chaos of tracking individual particles and adopting a fixed space, engineers gain the ability to systematically diagnose any fluid system using reliable spatial and temporal coordinates. To measure that control volume accurately, we translate physical space into a mathematical grid. We use mutually perpendicular spatial coordinates, x, y, and z, along with the independent variable of time, to map the velocity vector of the fluid. This matrix maps the three potential states. On the left, 1D flow relies on a single spatial coordinate. In the center, 2D flow requires two spatial coordinates. On the right, true 3D flow is a complex function of all three coordinates. These velocity vector equations form the baseline data. They are the initial inputs for the diagnostic engine, the series of tests used to classify fluid flow. Every complex fluid phenomenon observed in nature is simply a variation of these exact spatial and temporal parameters. Our first diagnostic test determines exactly how the fluid is changing. We do this by taking the partial derivatives of the velocity vector. In the top row, we test for time. If properties don't change as time passes, the time derivative is 0 and flow is steady. In the bottom row, if velocity remains constant between spatial points, the spatial derivative is 0, proving flow is uniform. This brings us to a frequent conceptual failure point in kinematics exams, the false assumption that steady flow automatically implies uniform flow. This matrix highlights the exact trap in the yellow box at the bottom. The classic scenario is a constant volumetric flow rate moving through an expanding pipe. Let's break down the physics. Because the amount of water entering per second does not change, the time variance is 0, meaning the flow is steady. However, because the pipe geometry expands, the velocity of the water must slow down as it travels forward. The spatial variance is active, making the flow non-uniform. Evaluating time and space derivatives entirely independently is the only heuristic that guarantees survival in high-stakes problem-solving. This independent evaluation resolves a common paradox. How can a steady flow undergo massive acceleration? The answer is that total acceleration is a composite of two separate derivatives. On the left, local acceleration results from a change in velocity over time. As the valve opens, flow speeds up, existing only in unsteady flows. On the right, convective acceleration occurs over space. The fluid accelerates strictly because the physical geometry changes. Adding these two distinct derivatives together yields the total acceleration state of the fluid. This table organizes how classifications dictate local and convective variables.
The ultimate exam shortcut. If a problem states the pipe diameter is constant, instantly eliminate convective acceleration. If discharge is constant, instantly eliminate local acceleration. Internalizing this matrix allows you to instantly strip away irrelevant data and isolate the actual physics of the problem. We now shift our focus from the macro velocity of the control volume down to the internal behavior of the fluid particles themselves. This diagram maps the thresholds. Laminar flow occurs when viscous forces keep particles in organized sliding layers. Turbulent flow triggers when inertial forces cause chaotic mixing. On the right, true rotational flow dictates particles rotate about their mass centers, physically demanding tangential shear stress. To analyze these complex vector states in practical engineering, we rely on three distinct visualization methods. Streamlines are drawn so a tangent yields the velocity direction. Path lines track a single particle's actual trajectory. Streak lines show the locus of particles passing a fixed point. Notice the critical exam rule. In a steady flow, all three lines are perfectly identical and superimpose. Knowing these lines converge in steady flow allows an engineer to deduce the system's state from a single visual cue, bypassing the math. Before assessing behavior or acceleration, an engineer must first verify the flow is physically possible. This is the function of the continuity equation. This volumetric diagram defines the core concept of discharge, represented by Q. For one-dimensional, steady, incompressible flow, the volume of fluid passing a section per unit time remains constant. We express this strictly as area 1 times velocity 1 equals area 2 times velocity 2. This subnote on the diagram expands the principle of mass conservation for compressible fluids like gases. Because the density changes as it moves, the equation must incorporate the density variable, ρ, into both sides of the balance. Transitioning from a simple one-dimensional pipe to an arbitrary three-dimensional flow field requires complex differential analysis. This differential flowchart traces the three-dimensional incompressible equation, dictating that the spatial gradients of u, v, and w velocity components sum to 0. The pinned exam insight delivers the physical litmus test. Any velocity field satisfying this equation is physically possible. Continuity is the non-negotiable law of fluid mechanics. If the velocity field does not balance to 0, matter is created or destroyed and cannot exist. Once continuity confirms a flow can exist, we construct its final architectural framework, the flow net. This architecture chart defines our final variables. On the right, the stream function, psi. Its existence is definitive proof of a continuous, physically possible flow. On the left, the velocity potential function, phi, exists only if the flow is definitively irrotational. For an irrotational flow to exist, it must satisfy the continuous mathematical condition known as the Laplace equation. This orthogonal matrix visualizes plotting these two functions. Equipotential lines and streamlines form a structured grid. Dictated by Cauchy-Riemann conditions, they must physically intersect at exactly 90 degrees. Because of this strict orthogonal requirement, a flow net cannot be drawn for rotational flow. To solve the 5 major model problems tested in APPSC, AEE, and GATE exams, we are going to build a diagnostic engine. This engine is a step-by-step testing sequence that classifies any flow field you encounter. This flowchart outlines the first diagnostic test: flow existence. Because matter cannot be created or destroyed, any physically possible fluid flow must satisfy the mass conservation principle, known mathematically as the continuity equation. Let's test a generic velocity field where u equals ax plus by and v equals dx plus cy. We take the partial derivative of u with respect to x, which leaves us with a. Then we take the partial derivative of v with respect to y, leaving c. For the flow to exist, the sum of these derivatives must equal 0. Therefore, a plus c must equal 0. Once you confirm a flow exists, you might be asked to find its stagnation point, the exact coordinate where the fluid comes to a complete rest. To find it, simply set both vector equations to 0. If x plus y plus 1 equals 0, and x minus y minus 2 equals 0, solving the system reveals a stagnation point at the coordinates of 0.5 and negative 1.5. Always run the continuity test first. If a given equation fails continuity, the flow cannot exist in reality. Any further calculations or tests on that equation are a trap designed to cost you time. To prove a fluid is ideal, we run test 2, the rotation check. We apply the 2D rotation formula, taking 1/2 of the partial derivative of v with respect to x, minus the partial derivative of u with respect to y. Watch out for this negative sign. It is the most common place to make an algebra error on the exam.
This grid displays a flow net. When a flow is both possible and irrotational, both phi and psi exist. The orthogonal conditions formula proves that when you graph these two functions, their lines will always intersect at exactly 90 degrees. The distinction is vital. The stream function proves the flow is physically possible, while the velocity potential function proves the fluid is ideal. Look at the yellow exam shortcut box at the bottom of this table. If a problem states that a pipe's diameter is constant throughout, there is no change in geometry.
you can instantly cross out the entire convective acceleration term without doing any math. The second shortcut applies to time. If the problem text specifies a constant discharge, the flow is steady. Velocity is not changing over time, meaning you can instantly cross out the local acceleration term. Let's put this together in an active recall test. You have a velocity field where v equals 3xi plus negative 3yj. Take 5 seconds. Does this flow exist? Is it rotating? And which functions exist? Applying conceptual rules to skip pages of unnecessary calculus is how you beat the clock on these exams. Let's look at the solution. This flowchart walks through the exact problem we just looked at. In step 1, we extract u as 3x and v as negative 3y. In step 2, we test for continuity. The derivative of u with respect to x is 3. The derivative of v with respect to y is negative 3. Add them together and you get 0. The flow exists. Next, we test for rotation in step 3. The derivative of v with respect to x is 0. The derivative of u with respect to y is also 0. The result is 0, meaning the flow is completely irrotational. Now we check the yellow box for our final verdict. Because the flow satisfies continuity, the stream function psi exists. Because the flow is irrotational, the velocity potential function phi also exists. Let's lock in this diagnostic matrix. Row 1, passing continuity, guarantees the stream function. Row 2, proving zero rotation, guarantees the velocity potential function. Row 3, look for keywords like steady to zero out local acceleration and uniform diameter to zero out convective acceleration. With this diagnostic engine internalized, complex equations resolve into a clear sequence of logical tests. You apply the constraints, eliminate variables, and reach the correct multiple-choice answer through a systematic proof.